It kind of presents as rational because there's denominators, but the denominators are all just numbers, not variables. So it is technically linear, but regardless, what would you do to get started on something like this? Connor, how would you attack this? Yep, okay, so go ahead and get them all to have a common denominator, sure. He said 30, so this gets multiplied by 6 and 6, by 15 and 15, and by 10 and 10. So he's going to have 18x over 30 minus 15x minus 45 over 30 equals 10x plus 20 over 30. Then what, Connor? Okay, combine these two terms together. So actually do the subtraction. Now be careful here because you are subtracting a binomial. So you have to be careful of that. You're going to do 18x minus 15x. That'll give you 3x. But then minus a negative 45 is going to be plus 45. Keep taking me through this, Connor. You can cross out those denominators, absolutely. And then we're going to solve this like a typical linear. So subtract the 3x over to the left, or over to the right. I don't know if you guys choose to bring the 10x over to the left. That's fine too. I just like to keep my x positive. So my x's are going to the right. My non-x's are going to the left. So I'm subtracting that 20. So I get 25 equals 7x. Divide both sides by 7. X equals 25 sevenths. Number 2 is rational because the denominator contains, but the process should still be the same. The one thing you would want to do though is anything that's factorable in the denominator, factor it first, because if you treat these as 3 separate denominators, your life's going to be a little bit uglier than it needs to. Usually if one of those is factorable, once you factor it, you realize that it at least has one of those factors already in common. So this, sure enough, factors into x minus 3 times x plus 1. So it actually has everything it needs. So that one we're going to leave alone. The first denominator is going to get an x plus 1. And the second denominator is going to get an x minus 3. And once the denominators are common all the way across, you can just forget about them. The equation that you're solving is going to be the equation that the numerator writes. So that's x plus 1. On the second one, the second numerator, I'm distributing a negative 2 to the x minus 3. So minus 2x plus 6 equals 8. When I combine like terms, I get negative x plus 7 equals 8. Subtract 7 from both sides. Negative x equals 1. And x equals negative 1. From here, we have to just double check that this is not an extraneous solution. What would make that an extraneous solution? Do you guys remember that word extraneous? Yeah? Go ahead, Abby.
So it's like when you find out like the restrictions, negative ones and restrictions, so it's like it's not.
Correct. It's an extraneous solution, which means it's not really one. Kind of fools you. It comes up with negative 1 and you check it, but it's not going to work. And it's not going to work because you did anything wrong in the process. Like sometimes you check and it doesn't work because you made a mistake. You didn't make a mistake. It's just the nature of this special type of function that has some excluded values that if you plug in negative 1, you're going to get an undefined term. So this is extraneous. And so there actually are no solutions. Which the types of functions you learned how to solve in Algebra 2, that was almost always something you should be looking for. Not so much for linear and quadratic functions, but for radical functions and absolute value functions, rational functions, log functions, exponential functions, all of those. Extraneous comes up because of the complexity of the problem. Number 3 is asking us to solve for f of 2. And the tricky part here is that f of 2 is currently in the numerator and in the denominator. And we somehow need to get all of our f of 2's together in order to isolate it. Okay, we got to get f of 2 all by itself without there being other f of 2's in the problem elsewhere. It has to be the only f of 2 in the problem, and it has to say f of 2 equals. Gosh, I can't remember the context that you had to do this last year. This is obviously even more complex because there's no numbers involved. Oh, I know. Let me back up. If you had a function that looked like this, and you were asked to write the inverse of that function, what do you have to do to write an inverse? First step. Very good. And then? Solve for y. So this is where what we're about to look at again in this problem, this skill of solving for y comes up when it's in two spots. One's in the numerator, one's in the denominator. Does anybody remember how you went about solving for y in a case like this? Give me your gut first step, John. By? Say it again. I don't think I'm following what you're saying. Aiden. Olivia. She's not here, right? Morgan. Marissa. What? You did this last year, right? You had to write inverses? For rationals? Go ahead, Joe. Okay, if you cross multiply, that's going to get rid of your denominator. So when you cross multiply, Joe, what are you going to make that? Like that? Okay. And when you cross multiply here, that's just y plus 3, obviously. Okay. And if I have to solve for y, what do you think, Mitch, you would do from here if you had to solve for y? So divide x on this side, and you'd have y plus 3 over x. And then what? What's making you stop? You were thinking you'd subtract the 3 from y, but you can't because of y? Right, so now you don't like doing that. So could you just subtract 3 here? And have this? What do you think about that? On this side? Right, that's not okay, right? Some people think that this is okay. They're like, what do you mean? I solve for y. Y is all by itself. But you can't, just like in English, you can't define a word using the word. You can't define y and solve for y using y. So the trick here is, how are we going to get all those y's together? Go ahead.
Does that have something to do with like the conjugate, like multiplying?
Nope. I guess I'm going to assume you guys did not do this last year, which is kind of surprising to me. So if we want to get all the y's together, what if this was a 7? What would you do? Right, you'd make it 7y minus 14 equals y plus 3. Would you have a problem with that? Probably not, right? Because that just looks like any other linear. You'd get all your y's on one side. So rather than being afraid of this x because it's not a number, we're just going to go ahead and distribute it so that that y is not locked up in parentheses. And then, again, if that was a 7y on the left and that was a 1y on the right, we would move one of them over, correct? If you're solving for y, you have to get all of your y terms together. So I'm going to subtract this y over to the left so that all my y terms, y being what I'm solving for, are all on one side. And I'm going to get rid of my non-y terms, the 2x. So what that leaves me with is xy minus y equals 3 plus 2x. And normally, again, if that x was a 7, I would just do 7y minus y is 6y, and life would be easy. Because it's an x, I can't really combine like terms the way I'm used to, but if you can't combine them, factor it. I can't combine these y terms. So then what I can do is factor out a y so that there's only one y in the problem. And now that I've gotten the problem to only contain a single y, now I can solve for it. I just divide that x minus 1 over, and I get y equals 3 plus 2x over x minus 1. I've solved for y in terms of x. Okie doke. So let's go back to the problem we're on. We're solving for f of 2, and it's in the numerator and the denominator. We are going to start by cross multiplying. That was a good first step. So I'm going to put this over 1. And when I cross multiply here, that's going to give me f times f sub 1 plus f sub 2 equals, and when I cross multiply the other one, it's just going to be f sub 1, f sub 2. I'm solving for f sub 2. It's on both sides of the equation, one of which is locked up in parentheses. So the only way to unlock it from those parentheses is to distribute. So I'm going to have f sub 1 plus f sub 2. And if I'm solving for f sub 2, I got to get all my f sub 2's on the same side together. So I'm going to subtract this f sub 2 over. And again, I can't combine them because it's not like it's 10 f sub 2's minus 3 f sub 2's. So if I can't combine them, factor out the f sub 2. And when that comes out in front, it's going to be f sub 1 minus f. And now, finally, there's only one f sub 2 in the problem. So I can get that all by itself by dividing this binomial over. And here's my answer, f sub 1 over f sub 1 minus f. So that was definitely more challenging than what at least I do with my Algebra 2 kids. We write inverse functions for every function that there is in Algebra 2. I'll kind of look more into why maybe you haven't done something like that. But regardless, so that was what we just did in that f sub 2. That was a step up from this. And given that you didn't even do that last year, that's a big step up from what you're used to. So make sure you put a little asterisk next to that and review that. Are we almost done? Oh, okay. I thought it was 20 for a second. All right, absolute value equations. This was not in the Algebra 2 curriculum, although I'm not sure if Mrs. Zig, did it with you. Did you do these last year? It's not in our curriculum, so if she did do it with you, it would have been her going above and beyond a little bit. This is an Algebra 1 thing, though. And it's just been a while, so I'm going to say that more likely than not, nobody remembers. But does anyone think they might remember? Okay. If you're solving an absolute value equation, you want to get the absolute value portion all by itself. So almost treat it like it's a 4y plus 7 and get the y all by itself. So we're going to subtract 7 over. Divide the 4 over. And I'm going to go down here because I didn't leave you much room. So the absolute value is now by itself. Okay? So thinking logically about this, rather than me just telling you what to do next, if I cover this up with my finger, it's the absolute value of something equals 3/4. There's two possibilities for what number could go under my finger. What are the two numbers that when you take the absolute value of them, you get 3/4? Yep. 3/4 and negative 3/4. Exactly. So whatever expression is in here could equal 3/4, and then we'd have a solution, or it could equal negative 3/4, and we'd have a solution. So I like to think of it, this step here, as branching this off into two separate equations. And this branching eliminates the need for the absolute value sign. We're kind of applying the logic of what an absolute value sign does right here. So either 1 minus 3/4 x equals 3/4, or 1 minus 3/4 x equals negative 3/4. And I'm going to solve each of these two mini linear equations separately to get two solutions. So on the left equation first, I'm going to subtract 1 from both sides. I get negative 3/4 x equals negative 1/4. Right? 3/4 minus 4/4 is negative 1/4. And then, Julia, how do I get rid of that negative 3/4 there to solve for x? Okay, but dividing by a fraction. No, cross multiplying is if we have like a, well, what would you write if you were cross multiplying it? Because that x is there. Yeah. On both sides. You could multiply by 4, but I like what she said. You divide by the coefficient. You divide by negative 3/4. But in math, we typically don't divide by a fraction. What's the equivalent of that?
You multiply by the reciprocal.
Right. That's the whole keep, change, flip thing, right? Rather than dividing by a fraction, we multiply by the reciprocal, negative 4/3, on both sides. So that handles the left, and you just have x equals, the 4's are going to cancel, the negatives are going to become a positive, it's just going to be 1/3. So there's one solution. The other solution, subtract 1 from both sides, and I get negative 3/4 x. Negative 3/4 minus 4/4 is what? Negative 3/4 minus 4/4 is negative 7/4. Yes? Again, multiply by the reciprocal. So x will equal, your 4's will cancel, your double negative will become a positive, 7/3. And we have two solutions for this. Okay? All right, so those last two obviously were fairly fresh. 5's just a straight up quadratic, so with any quadratic, get it equal to 0. So I'm going to subtract my 8x over and add my 15 over. And I've got the methods for solving a quadratic here. Factoring, should be the preferred method if it's factorable. Completing the square, I don't know of too many students over the years that actually choose that method in any circumstance. But if you do and you know it, then go for it. Or the quadratic formula, which you should know. If you don't have that memorized, you need to memorize it because that's not going to be given to you this year. So this particular one is factorable into x minus 5, x minus 3. Tee it up, you get x equals 5 and x equals 3. Okay, radical equations should be a review. Let me see if this one's a quadratic equation, should be a review. Number 8 is another absolute value. I'm just jumping to the ones just that I know I definitely want to get to. Number 8 is another absolute value equation, but it's a little bit trickier because there's a quadratic within that absolute value. So as far as isolating the absolute value, Nate, are you with me? That part's already done. So in that regard, it's easier than the one we saw on the front side. So we are immediately ready to branch. And this expression could equal 8 or it could equal negative 8. And each one of these branches, because it's a quadratic, is going to give us 2 solutions. So 2 solutions from this quadratic, 2 solutions from that quadratic. So we could potentially have 4 things that work here. Okay? I'm going to subtract my 8 over on this quadratic. Is that factorable? What do you think, Marissa? Yep. Very good. So our 2 solutions here are negative 7 and 1. On the right-hand side, I'm going to add 8 to both sides. And Mitch, how does this one factor? Right. In other words, x plus 3 squared. So on the second one, I have the same solution twice. X equals negative 3. Okay? In number 9, and I'll talk about number 6 at the same time, being radical equations, the first step I would write down if I was writing out steps would be isolate the radical, which is a no-brainer here, just adding 6. But on this last one that I put on here, if I say isolate the radical, well, there's 2 of them. Well, guess what? You can isolate whichever one you want, but you still isolate a radical. So I'm going to keep this one here, the one that I'm going to isolate, because it's already positive. So I'm just going to add this radical over. So I get root x plus 5 equals 2 plus root x minus 3. Do you remember solving radicals last year with 2 radicals in the problem? Did anyone? Does that anyone look familiar? Maybe. So once you isolate the radical, a radical, the idea is to square both sides. So when I square that on the left-hand side, the square root and the square are just going to cancel. When I square the right-hand side, I have to be careful and take a little more time here because I'm squaring a binomial, which really is going to mean I need to expand and FOIL. So the left-hand side is just x plus 5. That was nice and easy. The right-hand side, I'm going to do a 2 times 2 is a 4. 2 2 times the radical is just 2 times the radical. Another 2 times the radical is plus 2 times the radical again. And then root x minus 3 times root x minus 3 is just x minus 3. So when I combine like terms here, I've got the 4 minus the 3, which is 1, plus an x, plus 4 of these radicals. 2 of them plus 2 of them makes 4 of them. So the issue here when we had those 2 radicals to start is that once you finish that isolating the radical and squaring both sides, you still have a radical in the problem. But you only have 1 now. So we're just going to repeat from the top. We're going to isolate the radical. So I'm going to subtract 1 from the right. I'm also going to subtract x from the right. That's going to leave me with 4 root x minus 3s equals 4. Now, you don't have to divide away that coefficient. I could square both sides right now. And sometimes I would choose to. But here wouldn't be one of them because if I divide both sides by 4, it's going to still give me a whole number. Sometimes if you were going to divide both sides by 4, if it was going to give you a fraction on the other side, I would just, and I'll just show it to you for the sake of showing to you how it would work out either way, I would just square both sides right there. And I'm showing you this, again, in this problem I typically would have divided both sides by 4. But I'm showing you this on the right-hand side in case it comes up. If you ever have to square something and there's a coefficient out in front, that coefficient needs to be squared also. 4 squared is 16, and then the radical squared will just be that binomial x minus 3, but the kicker is you have to keep that x minus 3 in parentheses because that 16 is going to need to be distributed. You square the 4, you get 16. You square the radical of the binomial, you just get the binomial. It has to stay in parentheses. So you would distribute 16 equals 16x minus 48. Add your 48 over. And divide by 16. 4. And you want to check for extraneouses here for sure. Radicals are primed for extraneous. So if I go back up here, 4 plus 5 is 9. Square root of 9 is 3. Minus 4 minus 3 is 1. Square root of 1 is 1. 3 minus 1 equals 2. Okay, so that works, and we can hang on to that solution. Okay? So we'll stop there because these two are definitely easier. Isolate the radical, square both sides, and solve. This one you just have to square your binomial first. Treat it like a quadratic. Okay? Homework's there at the bottom.